We spent a decade manually editing 575,000 book pages, only to find that 10 clicks per book beat every scaling lever we tried. The author here, leading the Abtida Digital Library project in Pakistan, built a private community archive from scratch. They had no book scanner, no grant, and no digitization lab. Just a flat table, a Nikon D1000mm mounted above it, inexpensive Philips LED bulbs, and glass salvaged from a photocopier. For almost a decade, capture was the quick part, but after every shutter click, one of them still had to open every photograph in Photoshop and turn the spread into 2 finished page images. This was the manual bottleneck. They digitized rare Urdu books, including lithographs, dictionaries, and periodicals. When they wound down daily operations, they realized those 575,729 finished pages across 1,765 books recorded a decade of crop decision. They registered them back to their raw photos using SIFT and MAGZAC with conservative acceptance gates. They used the recovered geometry as supervision. The negative results are probably the most interesting part, for this sub, scaling from 378 to 572 training books, didn't move unseen book paths at 80. Neither did ResNet 50 1024 pixel inputs, or a spatial head. Per book error analysis showed why the failures were near constant offsets per volume. Our operator preferred a specific margin inset, which simply isn't present in the pixels of a new book. 10 operator corrected crops per book, took pass at 80 from 0.CE to 0.Basen. On held out volumes, 10 labels beat every scaling lever we tried. The core engineering feat here is how they turned finished Photoshop layers into training data. They didn't just take the final crops. They registered the finished pages back to their raw source photos. They used SIFT feature matching combined with MAGZAC for robust estimation, but, crucially, they applied conservative acceptance gates. This ensured they only kept the geometric transformations that were statistically sound. The recovered geometry became the supervision signal. This is a clever way to mine a decade of human preference without going back and re-annotating everything from scratch. The author notes that the archive grew out of a frustration with finding historic editions of Ghalib. Important volumes were out of print or sitting on private shelves. If the literature was inaccessible, they would have to find the physical books and build the archive themselves. This context matters because it explains the obsessive attention to detail in the manual workflow. The manual bottleneck wasn't just a cost center, it was a data generation engine. Every manual crop was a decision about what constituted a valid page. That decision is now encoded in the geometry. The negative results are the headline here. The team tested scaling the dataset from 378 to 572 training books. It didn't move the unseen book pass at 80 metric. They tried ResNet 50. It got a better training fit, but the held out performance was flat, and it actually got worse after calibration. They tried 1024 pixel inputs, no gain. They tried adding a spatial head, no gain. Per book error analysis showed why the failures were near constant offsets. Per volt all-loom, the operator had a preferred margin inset. This preference is a human decision, not a visual feature. It isn't present in the pixels of a new book. The model could see the paper, but it couldn't see the human preference for the margin. Scaling the data didn't help because the error wasn't in the data volume, it was in the signal type. The model was looking for visual cues that didn't exist. The error was structural, not statistical. So how did they fix it? They didn't add more data. They added 10 operator-corrected crops per book. They used an element-wise median residual. This took pass at 80 from 0.CE to 0.Basen on held-out volumes. 10 labels beat every scaling lever they tried. The author is genuinely interested in input on whether anyone has modeled document boundaries that depend on an invisible human preference rather than visible structure. Is there prior work on per-instance residual calibration like this? Their own next step is conditioning the model on the calibration examples directly. They want few-shot inset inference instead of a post-hoc median. This is a fascinating pivot. It moves from trying to predict the crop from the image to conditioning the model on a few examples of the desired crop. This acknowledges that the missing information isn't in the pixels, it is in the operator. The 10 clicks are a proxy for the operator's intent. The model just needs to learn to follow that intent, not infer it from the noise. For retouching, like stain and stamp removal, they kept the neural net to detection only. A U-net proposes the removal support, then classical OpenCV reconstructs the paper. Everything outside the mask is byte identical to the original. This is a crucial distinction for archival work. You want to alter only what you declare you are altering. Labels used remove, keep, and ignore states. Any erased Urdu diacritic vetoed deployment, regardless of IOU. The stricter label cut both improved mark IOU from 0.wulo to 0.nulin and got diacritic false positives to 0. This highlights the domain-specific challenge. Urdu script has diacritics that are critical for meaning. A standard IOU metric might say the crop is good, but if it cuts off a diacritic, the page is ruined, the routing rules are strict. One book, end to end. The Page Improver Studio handles the workflow. It routes uncertainty based on the diacritic check. If the diacritic is gone, the page goes back for review. This is a high-stakes quality gate. The community reaction is sparse but appreciative. One commenter pointed out that the project is pretty awesome. They also noted that the fact that so much of it is up on the Internet Archive is really nice. This suggests that the archival nature of the work resonates with the audience. The author is happy to answer anything about the method here, even though the code and weights release is still under archival review. They apologize for the delay. This transparency is valued. The full training recipes, label mining thresholds, and routing rules are in the reproduction contract appendix. This is a goldmine for practitioners who want to replicate the workflow. The author is not on the roadmap for a bigger backbone. They tested that. The missing information isn't in the pixels. This is a strong statement against the current trend of just throwing more parameters at everything. Sometimes the bottleneck is the human, not the model. The takeaway is clear. In specialized archival tasks, human preference can be a stronger signal than data scale. 10 operator corrected crops per book beat every scaling lever the team tried. The error was a near constant offset due to a preferred margin inset. This preference wasn't in the pixels, it was in the operator. The solution was conditioning the model on the calibration examples directly. For retouching, the hybrid approach of neural detection and classical reconstruction guarantees zero alteration outside the declared support region. The byte-identical guarantee is crucial for archival integrity. The diacritic veto is a domain-specific quality gate that standard metrics miss. This project shows that for high-stakes digitization, calibration and strict routing rules are more valuable than model capacity. The missing information isn't in the pixels, it is in the human. This is a lesson for anyone doing fine-grained document analysis. Don't just scale the data, calibrate the model to the human. The full breakdown is on the channel. Check the link for the reproduction contract appendix. That is the breakdown. 10 manual labels beat scaling. The missing information isn't in the pixels, it is in the human. Check the link for the reproduction contract appendix. Subscribe for more sharp AI analysis. See you next week. That is the breakdown. 10 manual labels beat scaling. The missing information isn't in the pixels, it is in the human. Check the link for the reproduction contract appendix. Subscribe for more sharp AI analysis. See you next week.